Explain of one keynote for 500 words without heading documentary-style words. Consider a simple cloud. It drifts, formless and silent, in the vastness of an open sky. Now, imagine that cloud is not made of water vapor, but of something far more elemental, cold, dark hydrogen gas and fine, cosmic dust. It hangs in the interstellar void for millions of years, a quiet monument to emptiness. But within that stillness, an imperceptible drama is unfolding. The force of gravity, the universe's great architect, is always at work, an insistent, whispering pull between every single particle. Slowly, almost reluctantly, a denser knot within this nebula begins to succumb to its own weight. It is a collapse of unimaginable scale and slowness, a gentle, inexorable fall inward. As this colossal sphere of gas contracts, a profound transformation begins. The energy of that fall, the gravitational potential energy of every atom drifting together, converts into heat. The core becomes a furnace, pressure and temperature climbing to staggering heights. For eons, it is just a protostar, a luminous, chaotic prelude to true stardom, shining from the violence of its birth pangs, but not yet from its own sustained fire. The critical threshold approaches, 15 million degrees at the core. At this moment of extreme temperature and density, something miraculous and fundamental occurs. The nuclei of hydrogen atoms, which have repelled each other since the dawn of time, are now forced together with such violence that they overcome their natural aversion. They fuse, marrying to form helium. This act of nuclear fusion unleashes a torrent of energy. It is a light born from the heart of matter itself. But more crucially, this energy radiating outward creates a powerful pressure, a fierce, radiant wind pushing against the endless, inward crush of gravity. For the first time, the collapse is halted. A perfect, precarious, and glorious balance is struck. The inward pull of the entire star's mass is perfectly countered by the outward push from the furnace in its core. This equilibrium is the star's defining state. It is no longer a collapsing cloud or a chaotic infant. It is a stable, luminous entity. It has achieved a cosmic adulthood, entering the longest and most stable phase of its existence, where it will spend the majority of its life. This delicate, dynamic tension between two of the universe's most fundamental forces, gravity's unyielding crush and fusion's radiant push, is the very engine of a star's life. It is the reason a star shines, and it is the balance that will one day, when the fuel depletes, be broken, setting the stage for the final, fateful acts of its story. Explain of two keynote for 500 words without heading documentary-style words. It begins in the profound cold and silence. Picture not emptiness, but a formless, drifting sea, an interstellar nebula, a ghost of former stars, composed of tenuous hydrogen and microscopic grains of dust finer than smoke. It hangs in the black, a cosmic cloud without a shape, for eons. The trigger is often a subtle, distant violence, the shockwave from a dying star's final cataclysm, or perhaps the gentle gravitational nudge from a passing spiral arm of the galaxy. This slight perturbation is enough to upset a fragile piece. In a region of slightly higher density, gravity, that most patient and persistent of forces, begins its work. The process is a slow, majestic collapse, a great falling, inward. A fragment of the cloud, light, years across, begins to contract under its own weight. As it shrinks, it fragments, and one of these fragments, a spinning, turbulent sphere of gas, becomes the focus. The physics are inexorable. As it contracts, it spins faster, flattening into a whirling disk with a growing, dense core. The potential energy of the collapse, the sheer gravitational cost of every particle drifting together, is converted into intense, brutal heat. The temperature at the center soars. For a time, this object, now a protostar, shines with a furious, angry light, but it is not yet a true star. It is an embryo, glowing from the trauma of its formation, a colossal sphere of chaos. The core continues to compact, a forge building toward its critical moment. Pressure mounts to almost unimaginable levels. The temperature climbs past 10 million, then 15 million degrees. Here, in this cauldron, the very nature of matter is forced to change. The hydrogen nuclei, simple protons which have existed in a lonely state since the early universe, now move with such frantic energy in the searing heat that they overcome their natural electromagnetic repulsion. They are slammed together with irresistible force. In a flash governed by the quantum rules of the weak nuclear force, they fuse. This is the moment of ignition, the nuclear alchemy that turns hydrogen into helium. The release of energy is instantaneous and profound. A wave of power surges outward from the core, not as an explosion, but as a sustained, radiant pressure. This new, fierce outward push finally meets the inward crush of gravity head on. The long collapse halts not with a jolt, but with the establishment of a perfect, dynamic opposition. The star finds its balance. The chaotic, infalling matter from the surrounding disk is either consumed or blown away by new stellar winds. What emerges from the swirling cocoon of gas and dust is no longer a violent protostar, but a stable, self-sustaining furnace. It has lit its own fire. It has achieved hydrostatic equilibrium, and in doing so, has officially been born. This new, steady light joins the billions of others in the galactic tapestry, a beacon ignited from cold darkness, ready to shine for millions or billions of years, its fate now sealed by the mass gathered in that initial, silent cloud. Explain of 3 keynote for 500 words without heading documentary-style words. Imagine the blueprint for a life, not written in words, but encoded in a single, fundamental number, its mass. The amount of material a star gathers in its natal cloud, the total heft of its hydrogen and helium, is the master key that unlocks every chapter of its existence. This initial endowment dictates the arc of a stellar life with an unyielding, physical logic, from the first flicker of fusion to the final, fading ember or catastrophic demise. It is the great cosmic divider, the architect of stellar destiny. The influence begins immediately. A star born with greater mass is a beast of fiercer gravity. This crushing weight forces its core to burn at a higher temperature and pressure, causing it to consume its hydrogen fuel not with the steady patience of a small star, but with the frantic, prodigious appetite of a glutton. The relationship is not linear, but cruel and exponential. A star with 10 times the mass of our Sun does not shine 10 times brighter. It may shine 10,000 times brighter, and it will exhaust its core fuel in a mere 20 million years, a fleeting, cosmic instant compared to the 10 billion year lifespan awaiting a star like our own. Here, mass dictates tempo. The more massive the star, the shorter, brighter, and more violent its life. This mass-driven destiny extends far beyond mere longevity. It governs the star's internal architecture and ultimate fate. In the relatively gentle heart of a star like the Sun, the churn of convection and radiation is orderly, slowly transforming hydrogen to helium in a stable, self-regulating process. But in the heart of a true stellar titan, the processes become layered, desperate, and extreme. As each successive fuel is exhausted, hydrogen, then helium, then carbon, the core contracts and ignites the next, heavier element at increasing temperatures. This layered burning, like a nested series of volatile furnaces, is only possible because of the immense gravitational pressure provided by the star's mass. It is this process that forges the heavier elements of the periodic table, from oxygen up to iron, seeding the universe with the raw materials for planets and, ultimately, life. Most critically, it is the final number on the balance sheet, the mass remaining in the star's core at the very end of its fusion chain, that scripts the final act. For a modest star, the journey ends with a quiet expulsion of its outer layers, leaving behind a white dwarf, a dense Earth-sized ember. But cross a critical threshold roughly 8 times the mass of our Sun, and the laws of physics demand a different conclusion. The core, having built up an inert iron heart, can no longer support itself against its own gravity. It collapses in a fraction of a second, not into quietude, but into the unimaginable violence of a supernova. What remains a city-sized neutron star or a region of spacetime torn asunder as a black hole is, again, a direct function of that remaining core mass. Thus, from the cradle to the grave, the life of a star is a story told by gravity, authored almost entirely by the single, decisive number it possessed at its birth. Explain of 4 keynote for 500 words without heading documentary-style words. The final act for a star like our Sun is not a violent explosion, but a slow, beautiful unraveling. For billions of years, it has maintained a stable, radiant balance, but all furnaces eventually exhaust their primary fuel. When the hydrogen in its core is finally depleted, the delicate truce between gravity and fusion is irrevocably broken. Gravity, the silent partner that has waited patiently for eons, gains the upper hand. The helium core, no longer supported by outward fusion pressure, begins a slow, relentless contraction. This collapse, however, releases a new surge of gravitational energy, heating the core to even more extreme temperatures, so extreme that it ignites a shell of hydrogen around the inert core. The star responds to this furious new internal heat in a dramatic way. It swells. It expands to 100 times its original diameter, becoming a red giant. Its color shifts to a cooler, ruddy hue, but its surface area increases so vastly that its overall luminosity grows monstrous. In this phase, it consumes any inner planets that dared orbit too closely. Yet this grandeur is unstable. The core, now a packed sphere of helium, continues to heat under its own contraction until it reaches a staggering 100 million degrees. At this point, a new and more frantic fusion process ignites. Helium nuclei themselves begin to fuse, creating carbon and oxygen in a flash known as the helium flash. This provides a temporary reprieve, but it is the last gasp of sustained fusion. The star's fate is now sealed. What follows is a period of intense, erratic pulsations. The star loses its grip on its own outer layers. In a series of gentle cosmic heaves, over tens of thousands of years, it expels its atmosphere, a vast shroud of glowing gas laced with the newly forged carbon and oxygen from its core. This expelled shell, illuminated by the fierce ultraviolet light of the exposed hot core, blossoms into one of the most sublime sights in the cosmos, a planetary nebula. These intricate, glowing clouds, rings, butterflies, and bubbles of multicolored gas are the star's final artistic testament, a brief, jewel-like display visible across light years. They are not planets, as early astronomers thought, but the funeral shroud of a star. At the center, revealed only after this great expulsion, lies the star's legacy, the white dwarf. This is the former core itself, a sphere of degenerate matter about the size of Earth, yet containing nearly half the original mass of the star. It is phenomenally dense. A teaspoon of its material would weigh tons on Earth. With no fuel left to burn, it no longer shines from fusion, but merely from residual heat, the fading glow of a banked fire. It will take trillions of years, longer than the current age of the universe, for this brilliant ember to cool completely into a cold, dark, crystalline sphere of carbon and oxygen, a black dwarf. This is the quiet, dignified end for the vast majority of stars, a slow fading rather than a dramatic bang, leaving behind a luminous ghost in a nebula and a dense, silent cinder drifting through the eternal night. Explain of 5 keynote for 500 words without heading documentary-style words. The death of the most massive stars is not an end, but a transformative cataclysm that seeds the future. Their lives are a frantic race against gravity, burning through successive layers of nuclear fuel, hydrogen to helium, helium to carbon, and so on, in a desperate, layered architecture of fusion. Each new element becomes fuel for a fiercer, shorter-lived fire, all the way up to iron. And here, the physics changes. Fusing iron does not release energy, it consumes it. So, when an iron core, heavier than our Sun but only the size of a planet, accumulates in the star's heart, the stellar engine suddenly seizes. The outward pressure that has supported the star for millions of years vanishes in an instant. What follows is one of the most violent events in the universe. With its support gone, the iron core collapses under its own immense weight at nearly a quarter the speed of light. In less than a second, it crushes down from a planet-sized object to a sphere barely 20 kilometers across, a neutron star. The implosion rebounds, sending a stupendous shockwave racing back outward through the still falling layers of the star. This shock, supercharged by a torrent of neutrinos pouring from the newborn neutron core, tears the star apart from the inside out. This is the supernova. For a few weeks, this single event can outshine an entire galaxy, radiating more energy than our Sun will over its entire 10 billion-year life. It is a cosmic forge of almost unimaginable intensity. Within this maelstrom, a crucial alchemy occurs. The extreme flood of neutrons in the supernova's fury enables a rapid series of nuclear captures, building elements atom by atom in minutes. Every natural element heavier than iron, the silver in a photographic emulsion, the iodine in our bodies, the gold in a wedding band, the uranium in the Earth's crust, is created in this brief, apocalyptic flash. Then, the explosion does something equally profound. It scatters these newly forged atoms. The supernovae blast hurls this enriched debris, along with the lighter elements cooked during the star's life, at tremendous speeds into the interstellar void. This material mixes with the primordial hydrogen and helium of the galaxy, enriching the great nebulae from which the next generation of stars and planets will coalesce. And the supernova leaves a relic, a monument to the violence of its birth. The core remains. If the progenitor star was massive enough, the collapse does not stop at a neutron star. Gravity wins completely, crushing the core past any known state of matter, creating a point of infinite density where the laws of physics, as we understand them, break down, a black hole. Its event horizon marks a point of no return, a tear in the fabric of spacetime itself. Whether a neutron star or a black hole, this remnant is the final, stark signature of the star's immense mass. Thus, the most colossal stellar deaths are generative acts of destruction. They create the very elements of life, seed the galaxy with future possibilities, and leave behind the most extreme and enigmatic objects in the cosmos. ensuring the star's final act forever alters the universe around it.